everyone, thank you so much for clicking onto the video. Today we're going to be looking at synthetic roots. So for an organic molecule containing several functional groups, we're going to be looking at the identification of individual functional groups and the prediction of properties and reactions. Then we're going to look at multi-stage synthetic roots for preparing organic compounds. So now we're going to look at organic synthesis. The synthesis of an organic compound can involve several steps, and these are factors that chemists aim for when planning synthetic roots. So synthetic roots are just routes that we can take to get from one organic compound to another. So for example, we could make an amine from an alkene. So the first factor we have to look at is using non-hazardous starter materials and processes that don't require solvents. And this is because solvents are often flammable and they're also toxic, and so we get some safety risks. And the second point is that if the solvent has to be disposed of after the reaction is complete, then we'll have a lot of waste which will be produced. The reason we want to use non-hazardous starter materials is that we want to limit the potential for accidents and environmental damage. The second factor we need to take into consideration are reactions that have a higher atom economy. And so chemists are also concerned with designing processes that aren't too wasteful. And if a reaction has a high atom economy, then we get less waste because more of the reactants will form the products. So processes with high atom economy and high percentage yields are preferred because they convert more of the starter material into useful products. And so we get less byproducts, and so we get less waste. And the last thing is that we want to have synthetic roots that have fewer steps. And this is because waste can also be reduced by designing synthesis routes that have as few steps as possible. And this makes sense because if you have a think about a really, really long synthesis that has lots and lots of steps, that means we get lots and lots of byproducts that we won't actually use and they won't be useful for us. So that will be waste compared to if we have a fewer steps, then we have fewer byproducts, and so we have less waste. So now we're going to look at the relationships between functional groups. So this is basically a mind map of how to get between different functional groups. And you should probably have this memorized in your head because it'll make it a lot easier to think of reaction schemes. So I'm first going to start off with the alkane. And we're firstly going to produce a haloalkane or a haloalkane from this alkane. And there's only one reaction that will make a haloalkane from an alkane, and that's free radical substitution. And that's where we have a halogen and also UV light, and we can add the halogen to the alkane to form this haloalkane. And we can also reverse this, and so this is why this arrow goes two ways. And now looking at a halogenoalkane or a haloalkane to an alkene, this is our elimination reaction, where we use some hot ethanolic to eliminate the bromine to form a double bond. And so that's how we get the alkene. So I'm actually going to put those in different colours. So for the free radical substitution, we need a halogen. And really important is that we need UV. And for this elimination, we need hot ethanolic sodium hydroxide. And then to get from a haloalkane to a nitrile, this is a nucleophilic substitution reaction. Because we're substituting the halogen with a CN. And so what we need is a CN minus ion. So how we get that is we add potassium cyanide followed by some acid. And then the next reaction is from this haloalkane to this amine. So this is again a nucleophilic substitution. And this is where we used ammonia as the nucleophile. And that was also our reagent. And now we're going to look at an alkene to an alcohol. So this reaction is a hydration reaction. And we have to add some water. And we would also need the presence of a strong H+ catalyst. So we would need an acid catalyst. And now we need to look at the haloalkane to an alcohol. So we missed that out before, but this is also a nucleophilic substitution reaction. But this time we're using an OH- as the nucleophile. And so the reagent we need is something like sodium hydroxide. But this time, instead of it being hot and ethanolic, like when we had the elimination reaction, we need it to be dissolved in water. So we need it to be aqueous and also cold. So we have cold, aqueous, sodium hydroxide, or potassium hydroxide. And so what we can do to get from an amide to a nitrile is dehydrate it. So this could be our dehydration reaction. So this is if we have the arrow going this way. And this free radical substitution is actually just from an alkane to a haloalkane. And the elimination reaction is from the haloalkane to the alkene. And so we have a dehydration reaction to go from the amide to a nitrile. And what we need is we need some phosphorus oxide. So we need to heat it with phosphorus oxide. And then to go from a nitrile to an amine, this is a reduction reaction. So we have a reduction reaction here. And this is our reduction that we looked at with the hydrogen and nickel catalyst. And to get from a nitrile to a carboxylic acid, this is a hydrolysis reaction. So here we have hydrolysis. And we need some water and also a H+ catalyst. So we need water and some kind of acid. And then this reaction here to get from acid chloride or an acid anhydride to an amide. So all of these acid chloride and acid anhydride reactions are all acylation reactions because these are both acid derivatives. So here we have an acylation reaction. And the nucleophile we use to form an amide is ammonia. So that is our reagent. And we can actually call these acylation reactions nucleophilic addition-elimination reactions as well. And it's the same thing. So we have nucleophilic addition, elimination. And so this is also an acylation reaction. But this time our reagent is water. And then to form an ester, we also have an acylation reaction. But this time our reagent is a primary alcohol. And now we only have a few more, and these ones are the ones which are a bit more simple. So first I'm going to look at the alcohol, aldehyde, carboxylic acid, and ketone. So to get from an alcohol to a ketone, what we need to do is oxidize it. And we need to remember that only secondary alcohols will oxidize to ketones. And how we do that is using potassium dichromate and a H plus ion, so a H plus catalyst. So if we're going this way, then we have oxidation, and if we're going this way, we have reduction. And so for reduction, what we use is sodium borotetrahydride, or LiAlH4. And for oxidation, what we use is potassium dichromate with a H plus catalyst. And this is the same for an alcohol to an aldehyde and a carboxylic acid. So primary alcohols will oxidize to an aldehyde, and the aldehyde will oxidize to a carboxylic acid. So going this way, we have oxidation, and here we have oxidation as well. And these are both using potassium dichromate with a H plus catalyst. So if we go in the other direction, so from an aldehyde to an alcohol, we have the same thing. So we have a reduction reaction here. So we use sodium borohydride or lithium aluminium tetrahydride. And we have to remember that we can only oxidize an aldehyde to a carboxylic acid, and we can't go the other way. We can also go straight from a primary alcohol to a carboxylic acid. So this would be an oxidation reaction. And we would use the potassium dichromate with a H plus catalyst. And then to get from a carboxylic acid to an ester, this is an esterification reaction. If we went the other way, it would be a hydrolysis reaction. And for esterification, we need an alcohol. And for hydrolysis of an ester, we need a H plus catalyst and also some water. And then to get from an ester to an alcohol, again, this is an esterification reaction. If we go from right to left and from left to right, this is a hydrolysis reaction. And so again, with the esterification, this time we need an acid, so we need a carboxylic acid or an acid derivative. And then for hydrolysis, we need water and H plus catalyst. So now we're going to have a look at the relationships between aromatic compounds. So all the compounds which have a benzene ring. So let's start off with benzene. So we have benzene in the middle. And now we're going to think about all the different things that we can produce from benzene. So firstly, we can go through halogenation. So this is where we add a halogen in the presence of a halogen carrier. So we can either go through bromination or chlorination. So if we go through bromination, we'll form benzene with a bromine attached. And so this is bromobenzene. And then we can also go through chlorination, and this will form chlorobenzene. So here we have bromination. And chlorination. And so we've reacted the benzene with some bromine with a halogen carrier, so it has to be a bromine carrier. So for example, we could have iron bromide. And then for the chlorination, we've added chlorine with the presence of a chlorine carrier, so some aluminium chloride, for example. And with benzene, we can also go through nitration, and this is where we add a nitro group. So what we form is a benzene ring, but this time we have a nitro group attached instead of one of the hydrogens. And so this is nitrobenzene. And this can then be reduced using some tin and hydrochloric acid to form an amine. So we can have phenylamine. So this has become benzene with an NH2 group. So this is phenylamine. And then with this phenylamine, we can then add some bromine. And so we'll form this benzene with this amine group, and then also 3 bromines. So this is 2, 4, 6 tribromo nitrobenzene. And so what we've done in the first step is reduced it. So this is reduction. And we've added some hydrochloric acid with a tin catalyst. And then for the second step, we've added some bromine. And then what we can also do with benzene is we can go through Friedel-Crafts, and we have either Friedel-Crafts alkylation or acylation. So firstly, looking at alkylation, what we do is basically adding an alkyl group to it. So we're adding a haloalkane, and so it's going to replace halogen from the haloalkane to form this alkyl benzene. So what we form is this benzene ring, and now we're going to have a methyl group attached to it. And so what we've done is gone through alkylation, or this is also called Friedel-Crafts alkylation to be more specific. And what we've done is added some chloromethane in the presence of aluminium chloride catalyst. And the final reaction we have with benzene is Friedel-Crafts acylation, and this is where we add an acyl group to this benzene. So we form something called an acyl substituted benzene. Or we could say an aromatic ketone. So what we form is benzene, and now we have a C double bond O attached and also a methyl group or an R group depending on what we reacted with the benzene. And then this can also go through reduction, like reducing an aldehyde or ketone, so reducing the carbonyl group to form a benzene ring. And then this time we have the carbon, and then we have an OH, a hydrogen, and then a CH3. So this is an alcohol. And so what we formed in the alkylation is this methyl benzene. And then here we formed 1 phenyl. So the ketone takes priority, so it becomes the root of the name. And so this is 1 phenyl ethanone because we have 2 carbons. And what we form after reducing this would be 1 phenyl ethanol, because we reduced this ketone to an alcohol, which is a secondary alcohol. And so firstly, to get the 1 phenyl ethanone, what we've done is we've added an acid derivative. So in this case, we've actually added an acyl chloride. So we've added CH3 COCl, and we've also added some aluminium chloride catalyst, and this is an acylation reaction. And then here we've reduced it, so this is reduction, and this is using some sodium borohydride. Now we're going to look at the reactions of phenols. So firstly, we're going to draw a phenol in the middle. And remember, phenol is just an OH group which is attached to benzene. So we have the benzene ring, which is C6H6. And then instead of having one of the carbons, we have an OH instead. And so this is our phenol. And the first reaction we have with phenol is bromination, and this is where we add some bromine. And because OH is a 2,4 directing group, that means that when we add the bromine onto the benzene ring, they'll be directed onto groups, onto carbons 2 and 4. And so what we form is the benzene ring, and we have the OH at the top still, and we'll have a bromine here, and also a bromine at the top here. And so what we've done is we've gone through bromination, and we've added some bromine. And another reaction that we can do is neutralization. So what this will form will be a salt. So we'll get the benzene ring, and then now we have the oxygen, but this is now a minus ion, and then this attaches to a sodium plus ion to form this salt. And so what we've done is we've neutralized it. So we've gone through neutralization, and we've added some sodium hydroxide, which is aqueous. Just going to write these in green because these are the reagents. And the third reaction we have with phenols is nitration. So this is exactly the same as the nitration of benzene, but just with an added OH. So what we form is the benzene ring, and OH at the top. And because OH is a 2,4 directing group, that means that the nitro group, so the NO2 group, will be either on the second carbon or the fourth carbon. So we have this product, or we can also get this product as well. So we get a mixture of both of these products. So we have the OH again, but this time the nitro group is on this second carbon. And what we've done here is we've gone through nitration, and the reagent is nitric acid. So now we can also label all of our molecules that we formed. So here we have 2,4,6-tribromo-phenol. So we're taking phenol as the root of the name. From the neutralization, we actually form a phenoxide ion. So because it's a sodium, we call this sodium phenoxide. And then from the nitration, we can form 4-nitrophenol, or we can form 2-nitrophenol. Now we're going to have a look at reagents used in organic chemistry. So firstly, we're going to look at oxidizing agents, and the oxidizing agent that we've looked at is potassium dichromate. So this is our K2Cr2O7, and this has to be acidified with a dilute sulfuric acid in order to oxidize alcohols. So what we can do with this potassium dichromate is oxidize primary alcohols to aldehydes and then eventually to carboxylic acids, or we can go straight from a primary alcohol to a carboxylic acid. And we also need to know that secondary alcohols are only oxidized to ketones. And then for reducing agents, we need to know that different reducing reagents have different capabilities. And that's why we've looked at 3 different reducing agents. So the first is sodium tetrahydride of borate, or we can also call it sodium borotetrahydride. And actually an alternative to this NaBH4 is actually LiAlH4. So either of these can be used. And it can be used in aqueous solution. And these reducing agents will reduce polar unsaturated groups, such as C double bond O, because we have the carbon, which is a partially positive atom, and then we have the oxygen, which will be partially negative. And this is because the oxygen is much more electronegative than the carbon. However, these reducing agents won't be able to reduce non-polar bonds, so such as the carbon-carbon double bond. And this is because it generates the nucleophile H-, which can only attack this carbon with a partially positive charge, but it's repelled by the electron-rich carbon-carbon double bond because we know that the double bond is an area of high electron density. The second reducing agent we have is hydrogen with a nickel catalyst. And this is what we use to reduce carbon-carbon double bonds, but not carbon-oxygen double bonds. And this is actually also used to reduce nitriles. So to get from a nitrile to an amine, we could use hydrogen with a nickel catalyst. And then the third reducing agent we need to know about is tin and hydrochloric acid. So this is used to reduce an RNO2 group to an RNH2. So for example, we could have a nitrobenzene and we would reduce this to a phenylamine. And then finally, we need to know about dehydrating agents. So alcohols can be converted to alkenes by passing their vapors over heated aluminium oxide or by acid catalyzed elimination reactions. So now we're going to look at how to work out a reaction scheme. So first of all, we start by writing down the formulas of the starting molecule and the target molecule. So we can see in the diagram that we have our starting material labeled A and our target material labeled X. And then the next step is to write down all the compounds which can be made from A. So these are B, C, D, and E, and all the ways in which X can be prepared. So we've got T, U, V, and W. And it's really important to keep the number of steps as small as possible, and this is to maximize the yield of the target. Sometimes you'll be able to see straight away that a particular reaction will be needed. So for example, if the target molecule has one more carbon atom than the starting material, then it's really likely that the reaction of cyanide ions with a haloalkane will be needed at some stage, as this is the only reaction we have where we can increase the length of the carbon chain by 1. So the example we're going to look at is the synthesis of propanoic acid from 1-bromopropane. So first, I'm just going to have a think about some reactions that I can have. So I'm going to start off with 1-bromopropane. So this is a primary haloalkane. So I'm just going to write that I have a primary haloalkane. And one of the reactions which comes to mind with primary haloalkanes, or haloalkanes in general, is nucleophilic substitution. And things that can act as nucleophiles are either negative ions or species that have that lone pair of electrons that can be donated to form a covalent bond. And so we can react primary haloalkanes with hydroxide ions, for example, to form an alcohol. So I can form a primary alcohol from this primary haloalkane, and this is by adding aqueous OH- ions. The second thing I can do is also a nucleophilic substitution reaction. So this time I can add cyanide ions. So if I add some cyanide ions, then I get a nitrile, and I have a primary nitrile, because this Cn- would replace the bromine. And then thirdly, I can also use ammonia as a nucleophile. So if I add ammonia, then I can form a primary amine. Because if you remember the nucleophilic substitution with with ammonia, we have a second ammonia nucleophile that comes and attacks, and so we remove one of the hydrogens off the NH3 to form an amine, which is NH2. And then the final thing that we can do with haloalkanes is we can go through an elimination reaction where we have the OH minus this time heated and dissolved in ethanol. So we have alcoholic OH minus, and this would be to form an alkene, because we're basically adding a double bond and getting rid of the bromine. So these are the two reactions that can happen with haloalkanes. We can either get nucleophilic substitution, or we can get elimination. And so here we have our nucleophilic substitution. And this one is our elimination reaction. And now I'm going to do the same thing, but with the target molecules. So what we can make the target material out of. So this time I'll start with the material on the right. So we have the end thing that we want to get, which is our propanoic acid. So we have a primary carboxylic acid, and ways in which we can form this primary carboxylic acid is, firstly, we can undergo oxidation. So we can form it from either a primary alcohol or an aldehyde, because we know that primary alcohol will oxidize to an aldehyde, and an aldehyde will then oxidize to a primary carboxylic acid. So we have, we can get this from an aldehyde, and this would be using the potassium dichromate with a H+ catalyst, or we could also get this primary carboxylic acid straight from the primary alcohol. And so again, this would be using our potassium dichromate. We could also get this primary carboxylic acid from a nitrile. So we could have a primary nitrile, and we would achieve this by adding some water with a H+ catalyst. So that's a hydrolysis reaction. And we could also get a primary carboxylic acid by using an acid derivative. For example, we could have an acid anhydride or an acyl chloride. And the way we would convert an acid derivative to carboxylic acid would be adding some water. And we actually also use some H+ as a catalyst. So now we can label our reactions. So these first two are oxidation reactions. And then this third one is a hydrolysis reaction. And this last one is an acylation reaction. So the nucleophile we're using is water. And now we can start to see what our reaction mechanism would be. So this is what we end up with. And now what we do is we can cross off all the things which aren't the same. And so basically what we need to do is we need to find something that is in common with both of these intermediates. So we can see that we've got this primary alcohol here, and we've also got a primary alcohol here. So this could be a possible intermediate. Or we have a primary nitrile here and also a primary nitrile here. So this could also be an intermediate. And there's nothing else in common, and so all of these four can't be used. So we don't do these. And so we're left with either a primary haloalkane going to a primary alcohol going to a carboxylic acid, or a primary haloalkane going to a primary nitrile going to a primary carboxylic acid. So now we need to decide between the two of them. And how we do that is, I'm just going to write out the different molecules, and we should begin to see why we can't use one of these methods. So we're going to start off with our primary haloalkane. So we have 1-bromopropane, which is CH3, CH2, CH2, Br. This is our 1-bromopropane. And so we've said that this can either form nitrile. So our primary alcohol would be propanol, or propan-1-ol, sorry. And this is because we've used the OH- as our nucleophile. And so we would have aqueous NaOH as the reagent. And then the primary nitrile that we would produce would be CH3, CH2, CH2, and then Cn. So this is butane nitrile, because we have 4 carbons. And what we've done here is we've added some Cn-. So what we do is we add potassium cyanide followed by some H+. So now if we have a look at the other side, which is propanoic acid, which is our target molecule. So we have CH3, CH2, and then COOH. So this is propanoic acid. And we said that we could form this either from a primary nitrile or a primary alcohol. So the primary alcohol would be propan-1-ol. So we'd have CH3, CH2, and then CH2OH. So this would be our first one. And how we would produce propanoic acid from propan-1-ol. We actually need to label this one as well. Is that we would add potassium dichromate with a H+ catalyst, because we're oxidizing it. So that would also be reflux. And the other way was using the primary nitrile. So we would have propane nitrile. So CH3, CH2, and then C triple bond N. And we could form this by a hydrolysis reaction, so adding water and a H+ catalyst. So this is our propane nitrile. So now we can see why we can eliminate one of these methods. And it's because here we have butane nitrile, but here we have propane nitrile. So they're not the same. And so we can't go through this method to get from 1-bromopropane to propanoic acid. And so we have to use propan-1-ol as the intermediate. So we've now found our reaction scheme. So what we have is that for step 1, we have 1-bromopropane, so CH3, CH2, CH2, Br. And this will form our CH3, CH2, CH2OH, which is our propan-1-ol. And this is 1-bromopropane. And what we've done there is we've added cold aqueous sodium hydroxide. So we always write down the reagent and not the nucleophile. So we don't write OH-, we write NaOH, which is the reagent. And then step 2 is propan-1-ol. So CH3, CH2, CH2OH. And this will go on to form our propanoic acid. So CH3, CH2, C double bond O, and then OH. So this is propanoic acid. And the way we do that is using oxidation. So we add potassium dichromate and a H+ catalyst, and this is a reflux.